Hey everyone, and welcome to This Explainer. Today, we're going to trace the incredible journey of power and uncover the hidden infrastructure that literally keeps our modern world lit. Have you ever driven past one of those massive, fenced-in yards full of gray towers, thick wires, and humming equipment and just wondered, what on earth is going on in there? Well, today, we are completely demystifying the electrical substation. You know, we totally take electricity for granted. You flip a switch and boom, the lights come on. But taking massive amounts of power from a generation plant and turning it into safe, usable energy for your home, that requires a highly complex middleman. Just think about it for a second. How does 400,000 volts of raw, highly dangerous power safely become the simple 440 or 240 volts that powers your street and your appliances? Okay, so here's our game plan for today. We're going to trace the full journey of a kilowatt, uncover exactly why we need substations in the first place, and explore the different types out there. Then, we'll map the power flow, break down the major components doing the heavy lifting, and finally, look at how the grid protects itself.
All right, let's jump right into part one, the journey of a kilowatt, from the plant to your plug.
Let's start way back at the very beginning of the macro power grid, long before electricity reaches your neighborhood. It all starts at a generating station. For example, picture a massive thermal power plant, burning coal to spin giant generators. That single plant might produce a staggering 1,240 megawatts of power. From there, this electricity is pushed onto the macro transmission system, traveling across those giant metal towers you always see along the highway, until it eventually reaches local distribution networks. But here's the catch. To make this incredibly long journey efficiently, that power has to be manipulated. Which brings us to part two, why substations are absolutely essential for fighting power loss. Now, you might be wondering, why don't we just send 440 volts straight from the power plant directly to your house? Well, it all comes down to heat and power loss. If we try to send power at a low voltage over long distances, it requires an incredibly high current. And as that high current flows through a conductor, it encounters resistance, which generates heat. It's basic physics. Power loss equals the current squared times resistance. Basically, a high current literally burns up as wasted heat energy along the way. If we didn't use substations to step up the voltage, your electricity would essentially roast the power lines before it ever reached your city. So to fight this, we drastically increase the voltage, which drops the current. Lower current means way less heat loss, and as a bonus, it lets us use much thinner, less expensive wires for transmission.
Okay, moving right along to part three, the different types of electrical substations. Because the voltage has to change at multiple stages, stepping way up for the long highway journey and then stepping back down as it gets closer to populated areas, we have different types of substations acting as stepping stones along the route. We categorize them by their function, like generating, transmission, or distribution, but also by how they're physically built. For instance, outdoor substations are super common. They cost a lot less to build, and it's really easy to spot a fault because all the equipment is right there in full view. The downside? They take up a ton of land. Indoor substations, on the other hand, are highly compact. We use them in crowded cities where space is totally at a premium, but they come with a much higher price tag and definitely make maintenance a bit trickier.
So let's look at part four, tracing the actual power flow.
How exactly does that massive voltage step down as it gets closer and closer to your neighborhood? Let's trace it out. The voltage drops sequentially to keep everything safe and manageable. Those massive transmission lines, they carry power at an incredible 400 kilovolts. A transmission substation receives that and steps it down to 132 kilovolts. Further down the line, a distribution substation drops it again to 33 kilovolts, which is usually what feeds heavy industrial plants. From there, it steps down to 11 kilovolts to run through local neighborhoods. And finally, that little pole-mounted transformer you see right on your street, that steps the 11 kilovolts down to the safe 440 or 240 volts that actually enters your home.
To keep track of this chaotic web, MEP engineers use something called a single line diagram, or SLD, to perfectly map out the power flow and equipment layout. Instead of drawing thousands of confusing, overlapping wires, an SLD uses simple, standard symbols. It acts as the ultimate roadmap, showing the incoming 33 kV supply, the transformers stepping it down, and all the 11 kV outgoing feeders distributing power to different local colonies. It's absolutely essential for anyone designing or maintaining a substation.
Now for the really fun stuff in part five, the major substation components.
Let's zoom in on a specific substation and look at the actual equipment doing the heavy lifting. The very first piece of equipment that incoming power encounters is the lightning arrestor.
You can kind of think of this as the grid's bouncer. If lightning strikes a transmission line nearby, or if a switching surge causes a huge unexpected voltage spike, the arrestor instantly diverts that dangerous excess voltage safely straight into the ground. This ensures the rest of the extremely expensive equipment doesn't just get completely fried. Right after the arrestor, we find the absolute heart of the substation, the power transformer. This is typically the most expensive and critical component on the entire grid. Its one and only job is to step the voltage up or down, in our neighborhood's case, down, while keeping the AC frequency exactly the same. By significantly altering the voltage, it safely changes the current and prepares the electricity for the very next leg of its journey. But what happens when that massive transformer needs routine maintenance? Obviously, a crew can't just walk up to a live high-voltage wire. That's where isolators come in. An isolator is a manually operated mechanical switch used to completely physically disconnect a section of the circuit. But here's the really important catch. Isolators do not have any arc quenching capability. That means you can only open that when the current has already been safely switched off by another device somewhere else. Despite being a relatively simple, cheaper manual device compared to the more complex automated components, the isolator is absolutely vital for human safety. When maintenance crews see those giant metal arms physically swing open, they have 100% visual proof that the power is cut off from the equipment they're about to work on. So you might be asking, if the isolator can't break a live current, what actually does? The answer is the circuit breaker. Unlike the manual isolator, a circuit breaker is a highly advanced automated switch. If there's a huge fault like a short circuit, the circuit breaker is designed to safely and instantly break the live circuit. For example, vacuum circuit breakers actually use a vacuum chamber to immediately suffocate and extinguish the massive electrical arc that tries to form when you suddenly snap a live 33 kV line. Now, for those circuit breakers to know exactly when to trip, they have to continuously measure the electricity. But how in the world do you plug a regular meter into a 400,000 volt line? Well, you don't. That would be a disaster. Instead, we use instrument transformers, specifically potential transformers to measure voltage and current transformers for current. They step these deadly, massive values down to incredibly safe, manageable levels. A potential transformer might step 400 kV down to just 110 volts, and a current transformer might step 2,000 amps down to just 1 or 5 amps. This clever trick allows standard, everyday relays and meters to safely monitor the grid's health in real time. Okay, here's a really cool, slightly surprising fact. Those giant power lines do a lot more than just carry electricity. They actually carry high-frequency communication signals, which allow different substations to talk to each other almost instantly. To manage this, a device called a wave trap acts as a filter. It ensures those high-frequency communication signals don't flow into the local substation equipment and get lost, all while allowing the standard low-frequency 50 or 60 hertz power to pass through completely uninterrupted. Let's wrap things up with Part 6, Protection, Control, and Safety. All of these incredible components, the transformers, the breakers, the arresters, they all ultimately tie back to one core purpose: ensuring safe, reliable, and continuous power. And the physical place where everything connects is called the bus bar. Think of it as the grand central station of the substation. It's a thick, heavy metallic conductor, usually propped up by heavy-duty post insulators because of its sheer weight. The bus bar collects all the incoming power and perfectly distributes it to the outgoing circuits, constantly balancing the load so one part of the city doesn't get fried while another part goes dark. So the big takeaway here is that a step station isn't just a dumb junction of wires. It's a highly active, constantly thinking control center. It balances the voltage, grounds deadly lightning strikes, isolates dangerous electrical faults before they can crash the wider grid, continuously monitors current, and routes power exactly where it needs to go to keep your lights on. Throughout this explainer, we've explored the incredible traditional one-way street of power delivery flowing from massive thermal plants all the way down to your wall outlet. But, our world is rapidly changing. As more and more of us add local solar panels to our roofs and smart grids literally push power back into the system, it completely flips the script. So here's something to think about. How will these traditional one-way, step-down substations need to evolve to handle the complex two-way traffic of tomorrow's energy grid? It's a massive engineering puzzle and one that is absolutely going to define the future of our power infrastructure. Thanks so much for joining me on this explainer, and keep your curiosity switched on.